Hello everyone, welcome to electric motors course. In this lecture we will discuss about the numericals on DC motors. So here is the numerical. A 250 volt DC shunt motor runs at 1000 rpm on no load and takes 5 amperes of current. The armature and shunt field resistances are given, it is 0.2 and 250 ohm respectively. Calculate the speed of the motor when loaded and taking a current of 50 amperes. Due to armature reaction, the field weakened by 3%. So let us understand the problem first and we will solve the problem. Okay, there is a 250 volts DC shunt motor which is running at 1000 rpm when there is no load connected to the motor. Okay, and it takes 5 amperes of current under no load condition. So the armature and shunt field resistance are fixed always. It is 0.2 ohm and 250 ohms respectively. So now we need to find out the speed of the motor when the motor is loaded, and when the motor is loaded it is taking a current of 50 amperes. Under no load it is running at 5 ampere. Now it is running at 50. It is taking 50 amperes. So under no load, when it is taking 5 amps, the motor was running at 1000 rpm. Now we need to find out the same speed when the motor is loaded and taking a current of 50 amps. And when the motor is loaded, due to the armature reaction in the DC motor, the field, that is flux, will be decreased by 3%, that is weakened by 3%. So we will see the whatever all the data given solution. So here voltage is given, that is 250 volt. No load speed, let me consider that as N0, it is 1000 rpm. And no load current, let me take it as I0, it is 5 amps. And we have the field resistances are armature resistance, that is 0.2, and shunt field resistance, that is 250 ohms. So these are the data given in the numerical. So now we already know the shunt motor, simple representation of the shunt motor. Armature winding and field winding both are connected in parallel. So this is the applied voltage to the motor. This voltage is 250 here, and armature winding resistance, field winding resistance, RA, RSH, and the current, it is drawing a current, means this is I0. I0, that is under no load condition it is I0, under loaded condition it is IL. And the current drawn by this field winding is ISH, current drawn by the armature is IA. So first we shall calculate the field current under no load condition. So field current, the equation for field current is, it is V is equal to ISH into RSH. So ISH will be equal to V by RSH. V is given, it is 250 volt, divided by RSH is also given, it is 250 ohms. So current in the field winding is 1 ampere. So current in the field winding will be always constant, because the resistance of the field winding is constant. So the current in the field winding, irrespective of whether the motor is loaded or not loaded, this will remain constant. Now when the motor is not loaded, it is taking 5 amps. In this 5 amps, 1 ampere is flowing towards the field winding, another 4 amps is flowing towards the armature winding under no load conditions. So IA0 under no load conditions is equal to, if you apply KCL at this node, applied current, that is IL is equal to IA plus ISH, or IA is equal to, it is under no load it is I0, or you can say IL0 minus ISH. So this will be 5 minus 1, it is 4 amps. The armature current drawn under no load condition is 4 amps. Now we shall calculate the EMF, back EMF under no load condition, let us consider EB naught back EMF. We know the equation for back EMF, that is in terms of applied voltage and the current through the armature winding and armature resistance. Since it is no load, IA naught into RA will be constant. So if you apply this formula, you can calculate the V is 250 minus IA naught is 4 into RA is 0.2. So this will be 249.2 volts. So this is the back EMF under no load condition. Same things we need to find out for when the motor is loaded now. So when the motor is loaded, it is drawing a current of line current of or load current of 50 ampere. Okay. So again the ISH remains same. The armature current drawn now becomes IA is equal to IL minus ISH. This will be 50 minus 1 is equal to 49 amps. Now when the motor is loaded, the armature is drawing 49 amps of current now. Now let us calculate the back EMF under this condition. Let us consider this as EB1. So this will be equal to, again applied voltage remains same, current is just IA into RA. So this will be 250 minus IA is 49 in this case into RA is again 0.2. So if we calculate this, we will get somewhere around 240.2 volts. So now we can observe here, when the motor is not loaded, the back EMF is high compared to when the motor is loaded. Now by using this data, whatever we calculated back EMF at no load and back EMF at when the motor is loaded, now we need to calculate the speed. We know the relationship between the speed of a DC motor, back EMF and the flux in the motor. That is N is directly proportional to EB by phi, that is flux in the DC shunt motor. Okay, so here it is mentioned that the flux is weakened by 3%. So under no load condition, let me take the flux under no load condition as phi naught under no load condition. And phi 1 flux under loaded condition. So it is mentioned that under no load condition the flux will be full. Under loaded condition, it is decreasing by that is 3%. 3% means it is 0.03 times of the original flux at the starting. So which will be phi 1, we can say phi 1 will be equal to, it is phi naught initial flux minus from this 3%, that is 0.03 times phi naught is decreased here. So this meaning nothing but now the flux under loaded condition will be 0.97 times of the original flux, that is under no load flux. So this is the flux now. So now by using this relation N directly proportional to EB by phi, let us consider under no load condition it is N naught E directly proportional to EB naught divided by phi naught. Under loaded condition, let us consider the speed N1 is directly proportional to EB1 divided by phi 1. So if you divide these two equations, N1 by N0, we will get N1 divided by N0 is equal to, it is EB1 divided by phi 1 into N2 will be, it is N0 is, it is in the denominator here, so this will be phi naught divided by EB naught. So if you substitute phi 1 as EB1, we know it is 240.2 divided by EB2 is 249. EB naught 249.2 into phi naught. Let us keep it as it is. Phi 1 will be 0.97 times of the phi naught. So phi naught gets cancelled here. So N1 will be equal to this N0 we can multiply here. So this will be into N0. So upon calculating, the speed of the DC motor will be 993.69 rpm. So this is the solution of the given problem.